Okay. Okay, so yeah, let me first and foremost thank the organizers for the invitation. I very much wanted to be there in person, but life is complicated. So yeah, so what I want to talk about is it's a very, I think, a very interesting connection between descriptive set theory and distributed algorithms or computer science in more general, and in descriptive set theory, it's Borel combinatorics in particular. So what are those things? Okay, so first I will quickly run through descriptive some things in descriptive combinatorics. Some of you, probably most of you, are already familiar with these things, but I just want to make sure that I don't lose anybody on this. So basically, the whole idea is that we consider graphs on Polish spaces, on large spaces, and we consider combinatorial questions about these graphs with usual notions of combinatorics like chromatic number, perfect matchings, etc. But the extra assumption is that the graphs are definable, so they are nice, and also the objects which we want to find are definable as well. So, for example, we want to find a coloring which is not any coloring of the graph, but it's a Borel coloring. Okay, meaning that the classes are Borel measurable. Okay, so this makes sense if there is a Borel structure on the vertex set of the graph. Okay, so yeah, so more precisely, so assume that we have a graph and we have a vertex set, and it's endowed with a Borel structure. Then we can say that we can define a notion of a Borel graph, right? Because a graph can be identified with its edge set, and as this edge set is subset of this product space, and this product space also has a Borel structure, and we can require that, or we can define a graph to be Borel in this edge set, if this edge set is Borel. And similarly, we can define Borel chromatic numbers when we say that, okay, so Borel chromatic number of a graph is a minimal n for which there is an n coloring, which is an addition Borel. Okay? And we will use I will use this chi-b of G notation for Borel chromatic numbers. And similarly, if there is a Polish, if the underlying structure is underlying space, the vertex space is say Polish, then we can say that, okay, we can ask what is a bare measurable chromatic number, or we can if there is a measure on it, we can mu, then we can ask what is the measurable chromatic number with respect to mu. Okay, and there are these definable notions, and let me show you an example which illustrates that these definable notions are somewhat different from their original counterparts. Okay, and this is probably the favorite example of simple example of a lot of people. So basically, okay, so what's written here? So we have the underlying space is going to be the 0-1 interval, and 2 points are fixed and irrational number, and 2 points are connected if this holds. So if x is equal, y is equal to x plus alpha modulo 1. But in some more intuitive way of just describing this very same thing is that you think about the circle as 1, and you fix a rotation with an irrational angle. Okay, and 2 points are going to be connected with respect to this graph if I can rotate one of the points to the other one using this irrational angle alpha. Okay, right, something like this. Okay, so this is, I defined a graph on the circle, and how does it look like graph theoretically? Well, graph theoretically, it's not very interesting, right? If you think about it, because alpha is irrational, you just take a point, you rotate it, you rotate it, you rotate it, jump, 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 jump. You can never jump back because of the irrationality of alpha. Okay, so every connected component is going to be a by infinite path. Okay, So in particular, since it's acyclic, its usual chromatic number is 2. Okay. Note also, this is something to check. It's an easy exercise that if you take any point and you iterate this irrational angle rotations, then the set which you get is going to be dense on the circle. It is not very hard to show. Okay, so this is the example, and my first easy claim is that its Borel chromatic number is not 2 as its usual chromatic number, but it's 3. Okay, so how do we show that? Well, let me show the lower estimate that its Borel chromatic number is greater than 2. Okay, so assume that it has a Borel 2 coloring. So here we have the circle, and assume that we manage to color this graph with 2 colors where each color class is Borel. Then, using say the Lebesgue density theorem, I can find an interval, a small interval, such that say 99% of the points in that interval are colored red. Okay. If you like the Baire category theorem more, then you can say that you can find an interval in which one of the color classes is comeager. Okay. So by the Lebesgue density theorem, you can find an interval which is well 99% is red. Okay, but look, what is going to be the trick? I rotate this interval with the angle alpha. Okay, and I go here. So this, of course, this rotation preserves the Lebesgue measure, right? So it must be the case that every point here, which is red, because it's a correct coloring, that the neighbors have to be blue, right? So in particular, 99% of this interval is blue, okay? And then I do this rotation again, then 99% is red, right? Etc. Okay, and you can imagine, because this is a 2 coloring, there is a strong algebraic sort of structure on this 2 coloring that if I jump, then it has to alternate, right? And right, so because of density, this density argument also gives you that there will be a rotation with if there will be some odd number such that if I iterate this rotation with alpha angles odd many times, then I because of this density argument essentially, then there will be a big overlap between these rotated copies. So I go, and there at some point there will be a big overlap. But this is a contradiction, right? Because if there is a big overlap and 99% here is blue, 99% here is red, then there will be points which are blue and red, which is not good. Okay, so fine. So we have this lower estimate. Okay, and what about the upper estimate? This follows from a more general result of Kekris, Soletsky, and Todorchevich from their early paper on Borel chromatic numbers. And this general result says that if I am given a Borel graph such that the maximal degree is every degree is, so this is the notation for the max degree. So every point has at most d many neighbors, then its Borel chromatic number is d plus 1. Okay, so in particular in our case, we know that every point has exactly 2 neighbors, so the Borel chromatic number is at most 3. Right. So we have this exact statement from this black box. Okay, so a bit different intuition is that, okay, so what do I have to do to color it? Because you can think about the question, okay, but I had a 2 coloring in general, like a classical notion of chromatic numbers, I had a 2 coloring. Well, how do you 2 color any pass? You pick a point, you decide that it's red, and then the neighbors are blue, then the neighbors of the neighbors are red, etc. And what you cannot do in a Borel way, picking points from connected components, right? So exactly this uses some sort of an axiom of the axiom of choice, that you pick a reference point, an origin on all these connected components. Okay, so this is the first simple example. And we are probably already familiar with this, but now I want to switch to something which might be new for some of the people. And this comes from computer science. So there is this so-called model, so-called local model of distributed computing. And first I will sort of give an intuitive explanation, and then it turns out that precisely it's a very simple thing. So assume that you have a very large graph. You have a very large network of computers. It's a finite network, but this N is imagined to be enormous, okay? And okay, so and there are some connections between the computers. Okay, so these points are computers, and these edges, these are connections. And okay, so in this model, in this computer science model, we allow the computer. It's the whole computation is divided into turns. And in one turn, what can a computer do? It can communicate with its neighbors. Okay, so you can send some messages here and back, and do some computation. Okay, and after some rounds, you have to decide on the output of this algorithm. So for example, a typical problem is what you want to solve in this graph theoretic problems like coloring, right? So for example, after some rounds, you want to say this computer must say that, okay, my color is red, and this computer must say that my color is blue, etc., and you want to solve the problem. Okay, and okay, so since this is distributed computing, it's a reasonable assumption that every computer has to run the same algorithm. So every computer, you cannot sort of treat the computers you cannot really distinguish between them. But then if you do just what I just literally said, you cannot distinguish between the computers, then the whole model becomes less interesting, because essentially, I mean, in few rounds, at least, the computers cannot do anything meaningful, because they cannot distinguish between really anything. They will output the same things. And so you have to, so there are symmetries essentially, potentially. And you have to break the symmetries. And there is this trick that every computer, and that's a very, very important thing, every computer has a unique identifier, a MAC address, if you wish. And and the computer or the algorithm can make the computation using these MAC addresses. An important thing is that you don't have control over the distribution of MAC addresses. So you have to write an algorithm. You have to write an algorithm which works in whatever t many rounds, outputs the correct answer, and no matter how the MAC address is distributed, the answer has to be correct. Okay. So this is the model. Okay. Yeah. So I already mentioned this, that we do not impose any bound on the length of the computation or the size of the messages, and we also don't have a control over the identifiers. And since there is no bound on the length of the computation, if the computer see the whole network, then again this whole thing becomes uninteresting. So somehow we want to optimize for algorithms which don't see the whole network, which just explore some local, like small neighborhood, explore the identifiers, and then output the correct solution to some, say, coloring problem based on that. Okay, so, but it turns out that, okay, so this is sort of the intuitive explanation, but it turns out that if you formulate this local model in this way, an algorithm is nothing else but any function which maps labeled, ID'd neighborhoods to colors, and that's it. So what you can do is you look around, you collect the IDs in your T-round neighborhood, and then you spit out the color. Okay, so that's it. Okay. And we want to solve a graph theoretic problem in a minimal number of rounds. That's the thing. Okay. And let me show you again an example of this. So assume that Yeah, so assume that the network looks like this. And the network looks like a very long but finite path. Okay, so there are n many computers. And I claim that it is not possible to two-color this in significantly less than n many rounds. Essentially, you need n many rounds to color this. Of course, n many rounds is sufficient because if I allow to work in n many rounds, I just explore the neighborhood from this computer. I know how far from the end I am, and then I just color based on the parity. That's fine. But if I'm restricted to work, say, in n over, I guess n over 4 is a very trivial lower bound. That if you are restricted to n over 4 many rounds, then you cannot solve this problem. Cannot solve two coloring. Why? Okay, so this is okay. So assume that this is n over 4, right? Right. So this means again, what is this local algorithm? It gets as an input these IDs. So for example, 6, whatever, 170, and 3. Okay, and this, based on these IDs, it has to output a color, say red. Okay, and then we go further, say here, and then okay, so red. This is blue. This is red. This is supposed to be, if it's a correct coloring, then this is supposed to be blue and this is supposed to be red. Okay, so for example, if I fill the rest of the IDs somehow, okay, and 5, then I will get here a red color again, right? Because I must. Okay, so if this algorithm is correct, then I must have. But wait, the problem is that using these neighborhoods, only these neighborhoods, I don't know how far. I don't know what happens here really. So it could be that the distribution of the IDs is as follows. Instead of this picture, there is nothing here. So the IDs are moved one here, and that's a contradiction because then the distance between these 2 points inside is odd, and then the color should be different. But using only this neighborhood, I cannot tell that, right? So this is sort of the intuitive. I mean, this is the explanation why you cannot do color in significantly less than n many steps. On the other hand, okay, so you might then think that okay, but this is an uninteresting model. You cannot do anything. But it turns out that if you want this recoloring, then there is a very fast algorithm for S recoloring, and this is a theorem of Coulomb-Wishkin. So in fact, there is a log star n round algorithm. What does that mean? Well, log star n is a function converging to infinity, but it's extremely slowly converges to infinity. So this is the definition. So it's an iterated logarithm of n. So the log star n is n if this inequality holds. For example, in practice, I guess log star n is never bigger than 5, maybe even 4, but 5 definitely. Okay, so this is a vast improvement on this n over, like essentially n. Okay, and what is the moral of the story? At least if we want to build this analogy between the two directions, is that okay, in the Boyle context, I wanted to pick points. I wanted to pick a reference point and then to color that, and it was impossible. And here, this is the very same thing happens. So I cannot pick a reference point because the network is too large. I am allowed to work in some small neighborhood, but I cannot pick anybody. I cannot pick an origin. Sort of there are these symmetries. Every point thinks that they are the same. So okay, so this is another example, and I hope that I managed to sort of convince you that there is a similarity here. But if you don't think that, then I will show you a theorem which shows that actually there is equality there in some sense. Okay, so instead of colorings, people in computer science like to consider these so-called locally checkable labeling problems. You can always think about colorings, but it's slightly more general. So what is a locally checkable labeling problem? It's the following. You have to color your graph. You have to label the graph essentially, label the graph with some say numbers or colors or whatever, and then you have to be able to decide whether this labeling is correct or not in a fixed radius neighborhood. So for example, coloring can be decided in one neighborhood. Okay, but this also covers, for example, perfect matching or edge coloring or all these usual graph theoretic problems. Okay, so this is a pretty large collection of problems. So we consider those, and then we can define this sort of classes of problems. Okay, so for example, I can say that whatever a problem is in Borel if whenever you give me a Borel graph, I can solve it in a Borel manner. That sort of problem. Okay, and similarly, I can define, say, bear and measure and whatever. And the point is that there is this index here f, which makes a lot of sense if you think about that. Of course, I won't be able to solve the problem in every graph. Say 3 coloring problem. You want to say, okay, so you want to build an analogy between paths in the Borel context, like infinite paths, and finite paths in the finite or local context, and then you want to say that, okay, what is the common thing in the Borel context with infinite paths and in the finite context with finite paths? Well, an infinite path locally looks like a finite path. So if you just look at it in some segment, then it's going to be the same. So the definition of this class really is that whenever you give me a definable graph, which is locally in this finite class, then I can solve it in a Borel manner, Baire measurable manner, whatever. Okay. And similarly, I can define these classes for this distributed computing based on the number of rounds. Okay, so there is this function, and we say that this local f problem is in local f if we can solve it in this many rounds in the local model. Okay. And yeah, so this is a general definition, but in this talk I will consider only trees. In fact, delta regular trees are locally delta regular trees. So every point has delta neighbors, and there are no cycles. You can say that there are no such finite graphs, and there is some technical thing which I don't want to talk about. But anyways, so the infinite version is always going to be delta regular trees. Every point has the. In fact, you don't lose anything if you just think about the 3 like regular infinite. Okay, right. And there is this very nice picture made by Vasek Rosszony and Honza Grebik about the connections, at least on the trees between these classes. You see that there is a very rich connection. So what does this mean, for example? This means that if, okay, so this arrow first of all means containment. And so, for example, this arrow says that if I can solve something in the local model in constantly many rounds, then I can solve it in log-staren many rounds, which is like a triviality, right? Because you have more rounds. But I think what's interesting is these, right? And with the red rectangles. So first of all, it says that some classes in the distributed world and in the Borel world, they just coincide, right? So, okay, so let me talk first about this rectangle about which contains continuous and log-staren. It turns out that this thing with the 3 coloring is absolutely not an somehow it's a fact really. So it turns out that continuous you can solve a problem in delta regular in a continuous manner if and only if you can solve it in the local world in log-staren many steps. Okay, so I mean, this is a very nice theorem and this established the connection between the 2 fields, but in retrospect, it might not be that surprising, right? Because sort of you think that these sort of local algorithms, they are really local and that corresponds to continuity. Okay, by the way, this is true for not only for trees, but in a very big generality. almost every graph in which you are going to be interested in. So it's a much more general theorem. And there is this other theorem, which is, I think, very surprising, which says that the bare measurably solvable problems coincide, at least on trees, here trees are very important, coincide with the log n time solvable problems. I mean, if you look at the two definitions of these classes, they are completely different, right? So it's I don't know. I mean, I think it's pretty hard to guess from the first side that this equality is going to be true, but it is true. Of course, the more honest version of this equality is that that there is a combinatorial condition. There is a combinatorial condition which is sort of equivalent to both sides. And then neither of these equivalences are very hard to believe, right? So actually this equivalence, that this combinatorial condition is equivalent to being able to solve on trees in a bare measurable manner. It's not hard at all. It's almost easy. And this part is hard. But anyways, using this combinatorial condition, maybe I write it down, it makes things less surprising, I would say. Okay, and yeah, and there is one other thing which is, for me at least, fascinating, very interesting. That Felix Weilacher in June gave a talk when he also came up with a completely different area, which is called recursive combinatorics. And in this recursive combinatorics, it turns out that this very same combinatorial condition plays a crucial role, and that is also a characterization. So my impression is that there should be a general theory of non-locality which treats all these things, because on the face at least, they all seem very similar to each other. So I don't know, but I don't know if it's possible or not, or maybe if we'll understand the whole theory much better, then we'll say that, okay, maybe it's just a superficial, it's a not deep similarity. But so far it seems that at least it's not excluded that they are literally exactly the same if one develops the right tools. Okay, so this was the general part of my talk. This is like this general connection between local and like the local model and Borel combinatorics, or distributed and descriptive. I don't know, maybe it's a good time to ask questions if there are any. I don't know if it's very complicated, then we
can. I think, like, as I said, we have a problem with the audio, so it's easier if we postpone the question at the end of the talk.
Okay, perfect. It's okay.
Thanks, Sultan.
Yeah. So nobody will interrupt me. This is fantastic. Okay, so now I want to show you a concrete example that this is not only an interesting connection, but you can transfer ideas. And this is what we call homomorphism graphs. Okay, so a little bit of motivation for why did we consider this all these things. Remember this theorem from the beginning, that if we have a Borel graph where the degrees are maximized by b, then the Borel chromatic number is at most d plus 1. Okay, and yeah, so just to repeat this terminology, this means that delta plus 1 coloring is in Borel T delta, right? Because this is a problem, delta plus 1 coloring, and every delta regular tree has degrees b, so this holds. Okay, this is just for the sake of terminology. But in the finite world, there is a much better version of this theorem. And in the finite world, it's called Brooks' theorem. It actually says when can you maximize? When can you maximize this? When can you achieve this bound, this delta plus 1 bound? And okay, so it says that unless something trivial happens, the chromatic number bound is actually delta. So what is this trivial obstacle? Well, Q delta plus 1. Complete graph on delta plus 1 many vertices has degrees delta, right? Has degrees d, but chromatic number d plus 1. Okay, but if this, and of course, if your graph contains that graph, then you can achieve this delta plus one. But Brooks' theorem says that otherwise, actually the bound is delta or D. Bound is D. Okay. And it was an open question whether there is an analog of Brooks' theorem in the Borel context. And Conley, Marx, and Tucker-Drob, they proved that if we, instead of Borel here, we consider bare measurable or measurable with respect to any Borel probability measure, then actually the answer is positive. So if there is no k d plus 1 inside the graph, then actually you will have decoloring, a bare measurable or a measurable decoloring. Again, this terminology says that delta coloring is in these classes because, yeah, so again, of course, delta regular trees, they do not contain k delta plus 1, kd plus 1. Okay, but what about the Borel context? And it was open for some time, I think for 10 years or so. What happens in the Borel case? And one hardship is about this theorem is that well, most of the tools for proving that some things, some graphs have a large Borel chromatic number, they are essentially just bare category and measure, as you have seen before with this circle. We used the bare category theorem or the Lebesgue density theorem, and that was it. And because of this statement, you cannot use those, right? So if you want to show that this is sharp, then you have to come up with something else, as Marx did. So yeah, so let me just quickly describe the example. So assume that we have a group and we have a generating set S, and this group acts. So it's gamma, and this group acts on this on the space X. Okay, so it moves around the points. Then there is a natural graph associated to this group action, and this is called the Schreier graph of this group action. We connect 2 points if there is somebody from the generating set which moves X to Y. Okay, so this is the Schreier graph, and then the most popular Schreier graph is the Cayley graph, really. And what's the Cayley graph? It's when gamma acts on itself by multiplication. Okay. And okay, so this is going to be our favorite group for the rest of the talk. So what is this group? This also can be described as a delta fold free product. Sorry. So it's the delta fold free product of Z2s. Okay. And I will draw just the Cayley graph just to illustrate it. So here is one, and I can move with these generators. Okay, so for example, the first generator is A1, and the second generator is A2, and the third generator is A3, and then I can move A1 with A3 further, and I can move A1 with A2 further. But if I use A1, I just go back, so I don't get a new edge. So if you draw this graph, it's going to be really 3 regular tree. Okay, so it grows. Okay, I won't draw the colors. And also note that there is an actual coloring of the edges, right? Which edge corresponds to which generator. Okay, so I just write it down here to remember that K gamma delta is a deregular, it's a delta regular tree. Okay, fine. So this is one graph example of a Schreier graph, and the other important example for us is going to be the left shift action of gamma on n to the gamma, which is slightly more complicated. So this is the definition that, okay, so first of all, an element of n to the gamma, what is that? I label the points of gamma, elements of gamma with natural numbers, right? So this is x. And this is a function from gamma to the natural numbers. And then what is the action? Well, I got to come up with a new function. So this evaluated is at delta is going to be x evaluated at gamma inverse times delta. Okay, and okay, so this is nice, but the intuitive meaning is the following. So an element of this n gamma is sort of a labeled version of the group. So there are some numbers written on it, right? Something like that. Okay, and there is a root, and the 2 points are connected. So 2 labelings are connected if one arises from the other by moving a root to the neighboring. To a neighboring vertex. So if you think about it, this is what happens. So there are these labelings, and okay, so this is sort of x, say evaluated at 1, it's 3, and then you move the root, and this is going to be say gamma times x here. Okay, so remember label 3 is and you move the root. That is the new graph. Okay, and what Marx proved that if you consider the part on which this action is free, then actually there is a Schreier graph there, right? I just defined the Schreier graph. Then first of all, it's acyclic, so it's acyclic. It's a nice, decent Borel graph, and delta regular. It's not hard to check these things, and but the point is that its chromatic number is delta plus 1. Okay, so in fact, surprisingly, the upper bound is, even in the case of acyclic graph given by Kekri-Seletsky and Todorchevich, is sharp. Okay, so again with this terminology, delta coloring is not in Borel-T delta. Okay, so as I mentioned, the remarkable thing about this idea is that it cannot use measurement category. So the new tool which Andrew came up with was the Borel, using Borel determinacy theorem. So this uses Borel determinacy. Okay, fine. And I won't be able to go into details. I just want to say a very, very high level, like the very, very basic step of the whole proof is that, okay, so how do you use Borel determinacy theorem? Assume that there is a delta coloring. So assume you work towards a contradiction. So assume that there is a delta coloring and you define some games. And there are these 2-player games that 2 players come up with an element of this space. Okay, so 2 players come up with the labeling with an x in n to the gamma delta, and somehow you get into trouble from the existence of winning strategies. Okay, I didn't tell you too much, but the point is that, okay, so how do you get into trouble? You can imagine that often it's strategy stealing argument. So you can imagine an argument which says that, okay, because of the Borel determinacy theorem, one of the players has a winning strategy, but then you use the player's winning strategy against itself somehow, and then you get into trouble. Then you get a contradiction. Okay, so this is a very, very, very high level idea of the proof. And what we wanted to do is to push down this idea, this Borel determinacy idea, to the local model. Okay, so we know that there are these games, and in fact there was this very interesting similarity between a model, between a technique in the local model which is called the round elimination technique, and this game technique. And I have to say, I still don't quite understand the full extent of the similarity. I think it's something to work on, because there is this very sort of convoluted, complicated technique in the local model, and that gave them very, very nice new results. But it then turned out that it's very similar to the determinacy technique, but it's still not clear the exact similarity. So there is, I think, an open question over that. Anyways, so the point was to somehow adopt this Borel determinacy technique to the local world. Okay, and there was a problem. Okay, I thought that it was a sort of minor, really a technical issue, and it's uninteresting and all, because otherwise everything worked out. You can play the games, you can do everything. So for example, play the games. Okay, so here we labeled by natural numbers, right? The two players labeled by natural numbers. Now what you will do in the distributed setting? Well, in the distributed setting, you have these IDs, which are also natural numbers. So the two players should label by IDs, right? And that's the version of in the local world. So so the two players, they play IDs, and you have this tree in the local world, and then you give IDs, and then you get into trouble because of some argument. But the point is that the problem was that that really when you do these strategy stealing arguments, you cannot really ensure that the IDs are unique. Remember that in the definition of the local model, this was a very important feature, that the IDs have to be unique. Otherwise, the whole thing is something else. And using these games, I mean, the whole thing just wouldn't work out if you just use these games naively because of this non-unique IDs. But they already had, so this was sort of our plan. We wanted to adopt Mark's method to local model, and there is this, okay, so they had a trick to guarantee the unique IDs, or at least unique to the extent which it matters. So that trick was that, okay, so assume that you have this tree. Okay, so again, this tree comes with an edge coloring, right? It looks like this somehow. Etc. Okay, and instead of labeling with any numbers, you imagine that the numbers form a graph. So here is this n, and they form a graph. Okay, so that there is this graph. In fact, not n graph, but an edge colored graph. But not so. There are some conditions on this graph, so it looks something like this. Yeah, and I use the same color on purpose. Here, there is no same color on purpose. And what is the property of this graph? That every cycle here is very large. Okay, so this graph has large curves. Okay, and the idea, and this ID graph trick is the following: instead of labeling just with IDs, what we do is imagine that these IDs form this graph. Okay, so Vn, and we label with vertices of these graphs. Okay, V1. Okay, maybe this is V1, and with an extra condition that we have to build a homomorphism which also preserves the edge colors. Okay, so here is V1. Okay, so what can be the image of this point? Well, V1 has some neighbors, say V31, V23, whatever. But we have to map this guy to one of its red neighbors. Okay. Okay, so this is the point. And if you think about that, you cannot come back. That's the trick. So what is the point with this injectivity? Well, I mean, I color with V1, and then I color the neighbor also with V1. Okay, fine. Then I came back. But here, if you have to preserve homomorphisms, and this is large girls, you cannot come back very quickly, right? You have to go through this cycle over that. Okay, and that is a basic ID graph trick which they had in this local model. Okay. Okay, fine. And then it's sufficient to give you the contradiction in the case of adaptation of this Borel determinacy technique to the local model. Okay, so yeah, so large goods graph, the homomorphism should preserve edge colors, and then you cannot come back too quickly. Okay, fine. But this gave rise to, I think, in a very natural way, we can go back to the Borel context and use the very same idea in the Borel context to come up with a very new object, which we call the homomorphism graphs. Okay, so think about it. What happened before? We had a finite graph, and we considered all the homomorphisms to some other graphs. So why can't we do the same in the Borel context? Okay, so what's happening here? So, and this target graph to which you build a homomorphism, it doesn't have to be finite. It can be Borel. It can be large, right? So here is the precise definition. So remember, we had this n to the gamma, and we have this Schreier graph on that space, right? But we can replace this n with any vertex set of basically any poly space, and we still get a very nice. We have a very nice space. We have a Borel space, for example. Okay, and so we have this Schreier graph, and the trick is that we restrict this Schreier graph to that part where, okay, so an element of this Schreier graph, a vertex of this Schreier graph, is a labeling of this gamma with the elements, with the vertices of VH. And we restrict this Schreier graph to the part where these labelings happen to be homomorphisms. In other words, when there are these two players, they are required to build homomorphisms. That's the trick. And we end up in this part. Okay, and this is what we call homomorphism graph. And why is this any good? Well, it turns out that there are very nice features of this homomorphism graph. In particular, it turns out that if I start a Borel graph, I will call this the target graph. Then, for some reason, the properties of the target graph the homomorphism graph inherits some properties of the target graphs. For example, if the Borel chromatic number of the target graph is low, is less than delta, then the Borel chromatic number of the target graph of the homomorphism graph is also less than delta. This is actually very easy. This is almost from the definition. On the other hand, which is sort of much less trivial, and it goes through Mark's method, Mark's argument, is that if the homomorphism graph has large chromatic number, if the target graph has large chromatic number, and this is something worse than Borel, anyways, if it has large chromatic number, then the Borel chromatic number of the homomorphism graph is also large. Okay, so there is this reflection of the properties, and this homomorphism graph is nice because it's still, yeah, so it's still deregular, defined. So this is a delta regular graph, and I could have started with any very complicated graph as a target. Okay. Okay, fine. Why is this any good? Some applications. So, for example, there is this central notion in Borel combinatorics and then dynamics in general, which is called hyperfiniteness. So we say that a Borel graph is hyperfinite if it can be expressed as a union, as an increasing union of graphs with finite connected components. And there was this result of Conley, Jackson, Mark, Seward, and Tucker, where they proved that hyperfiniteness doesn't really help with Borel with combinatorics. So even if your graph is hyperfinite, you can have a large chromatic number. You cannot solve some combinatorial things like there is no analog of the Lovász local lemma, etc. And now we get this freely essentially. So we get this theorem in a very easy way because hyperfiniteness in the right context also inherited by the homomorphism graph. So what we do is we take a graph with large chromatic number or complicated combinatorics and hyperfinite, but it doesn't have to be delta regular. It doesn't have to be anything. It can be very large, like G0. Think about G0 if you know what that is, and then take the homomorphism graph, and then it automatically is going to be hyperfinite, but the chromatic number is still inherited. Okay, so this is one nice thing about the homomorphism graph. The other nice thing is that okay, so there was this result, and I guess this is the very short complexity part of the talk. So there was this theorem which we proved with Stevo, that if it is impossible to decide the chromatic number of a Borel, the Borel chromatic number of a Borel graph. Okay, what does that mean? It means that if I take the collection of acyclic Borel graphs with even acyclic Borel graphs with Borel chromatic number at most 3, then this is a sigma 1 to complete set. There will be no meaningful characterization, this set. But these graphs, which we constructed there, by the way, this also used the Galvin-Prickly theorem and Ramsey theory, and these graphs, in a sense, were essentially non-bounded degree. So that the degree was it had arbitrary large degrees. But the trick is that, okay, now we have this sigma 1 to completeness result, and we use the homomorphism graphs. If you like to think about it that way, this homomorphism operator, and you get that already 3 regular acyclic Borel graphs are complicated. Okay, so with chromatic number at most 3 are complicated. So it's very hard already to decide the chromatic number. And this also gives an answer to one natural question after Mark's result, because, okay, so remember that in the finite case, Brooks' theorem was that unless something trivial happens, unless you find something trivial in your graph, the chromatic number is going to be small. And you can ask after Mark's result that maybe this is the only obstacle. Mark's graphs are the only obstacle, that if you don't have a copy of Mark's graph inside your graph, then the chromatic number is going to be small. But this complexity result excludes that as well. So in a strong sense, there is no analog of Brooks' theorem. There is no obstacle really. Okay, so there is no like simply describable obstacle. Okay, and yeah, and let me mention another thing. Also a natural question with this result, and this is sort of a slightly perpendicular direction, but I wanted to point out that as well, that if you, okay, so you can ask what happens if you replace 3 here by something else. And if you replace 3 by 2, then it turns out that this completeness result is not true anymore. So this is going to be pi 1, 1. So in other words, it is easy to decide whether a graph has a Borel 2 coloring or not, but it's hard to decide whether it has a 3 coloring or not, and everything above 3 is also complicated. And by the way, how to decide whether it has a 2 coloring? Interestingly, if you remember this cycle example in the very beginning, a version of that has to be necessarily contained in your graph in order to have a large chromatic number. Okay, fine. And okay, so there is this complexity result, and it's of course very interesting because from the perspective of the finite things, because in the finite world we know that 2 coloring is polynomial, 3 coloring is NP complete, right? So there is this reflection, this thing over there. And Raimi Thornton recently worked on the question whether you give me an LCL, is it hard or this locally checkable labeling problem, is it hard to decide or easy to decide? And of course, yeah, so in the finite world, they know that this is a very nice recent result, which I think it's from 2017. Then actually there is a nice characterization of which LCLs are easy to decide and which LCLs are hard to decide. Meaning that some of them are polynomial and some of them are NP complete. And it seems that the very same phenomenon is going to happen in the Borel context. But in the Borel context, it's good because we can prove that they can be distinguished, right? In the Borel context, we know that sigma 1, 2 complete sets are hard. In the finite context, NP can be P, right? Nobody thinks that. But anyways, it's interesting that in the infinite context, there is a provable distinction, and it's the very same distinction, and then in the finite context, but there it's not provable. Of course, there is no implication between them, but yeah, just an interesting fact. Okay, and let me finish with some open problems. So first of all, this is connected to homomorphism graphs. I think this is for me, it's one of the most important open problems right now. That we want to understand what properties of H could guarantee that the homomorphism graph is hyperfinite. Okay, and then it's far from being clear. It's not very apparent how you can generalize Mark's method. Mark's method works for colorings, but hyperfiniteness, it's absolutely not clear. And the other question, which is very much related, that if you replace here H, you can have large graphs. you can have non-locally countable graphs. And for non-locally countable graphs, there is this notion of hypersmoothness. So assume that it's not hypersmooth. Is it true that the homomorphism graph is not hyperfinite? So what is the relation between these things? So these are more concrete open problems, and I would like to formulate finally two things which are I think rather natural questions. So remember this picture, okay? If there was this picture, at least for trees. So here it is. But we know that there is an equality over here, there is an equality up there, but there is nothing corresponding to Borel here. So the question is there a computational model in the distributed world which would correspond to the Borel, say, hierarchy there? And I recently became somewhat optimistic about this question. The downside is, of course, that this is not really going to be local. And maybe this is, for that reason, it's not going to be interesting for the people in computer science. But anyways, that should be, I guess, the open question here, that whether there is an analog of the Borel hierarchy in distributed computing. And the other related question is that, remember, okay, so we could adopt this determinacy technique to the finite context, but we know that continuous corresponds to local O of log star n. We have this correspondence, and we know that continuous determinacy is not an interesting theorem. I mean, it's interesting, I guess, but it's far from being that deep as smart as the full Borel determinacy. I guess you can actually prove this. That this is really deeper. You have to use the power set operation or whatever. And the point is that my guess is that it should give, the Borel determinacy theorem should give some very strong finite theorems, because now we have that the continuous determinacy gives the local O of log star and lower bound, but the full Borel determinacy should give something much stronger in the finite world. And I don't know what that is, and I don't know if even if that is possible or not. But I think it's an intriguing direction. Okay, that's it.
Okay, thanks a lot, Zoltan. So we're gonna try something for the questions, and hoping that it doesn't make too much feedback. Okay, can you just go a few slides before with the sigma 1-2 completeness result? So Stevo is asking, is saying that in the previous theorem you're working with the shift graph, and he's asking what is the kind of graph you're working in the second theorem?
So it's the homomorphism graph of the shift graph. So you take this homomorphism operator and you apply it. So you plug in here as H the shift graph. Yeah, so this is the nice feature of the homomorphism operator, that it gets you 3 regular graphs from large graphs.
Okay, Philip Welsh has a question.
Referring to the same theorem, when chromatic numbers less than or equal to 4, I think you said something, but it wasn't clear.
Okay, so Philip Welsh is asking, you said something when the Borel chromatic number is less or equal to 4, but he wants to know precisely what.
It's also sigma 1-2 complete. So for any other any chromatic number other than 2, and okay, all of 0, yeah, strictly less than all of 0, but that doesn't matter here. So for 2, it's pi 1 1, but otherwise it's sigma 1 2 complete. Was that the question?
Sorry, Zoltan. I'm not sure I fully understand the question. So we're gonna try something and hope there's no. All right.
Write your questions. Yes.
What you want me to do? Write it. Speak. Okay. So, I was wondering about. I was just wondering about cases where you're not using full Borel determinacy, but perhaps just determinacy down at the, sigma 02 or sigma 03 cases, where, these are results that are provable in second order number theory. I was just wondering whether there was anything comparable in these results here where you didn't use full Borel determinacy.
I have no idea. I think it's a very interesting question. I don't know.
Okay,
So,
thanks.
Yeah, so I guess I don't want to say something stupid. I'm not sure about the situation. There was some remark in some footnote in some paper whether full Borel determinacy needed for this chromatic number result. My recollection is that it is not, but still you need something but yeah.
Okay, thank you.
Other questions?